Hi, everyone. Thank you for being here and joining my talk. My name is Jiacheng Wu, and I am excited to present our work titled HoneyComb, a parallel worst-case optimal join on multicores, done in collaboration with my advisor Dan Sushiu at the UW. Our goal with HoneyComb is to bring worst-case optimal joins, or WCOJs, into the era of large multicore machines, making them fast, scalable, and practical. Joins are the core operations in databases, and parallelizing them is key to scaling analytics. Here, our system HoneyComb mainly focuses on the worst-case optimal joins. Worst-case optimal joins outperform traditional joins, especially on cyclic queries, which are common in graph workloads and knowledge graphs. However, the worst-case optimal joins aren't easy to parallelize. Existing parallelization approaches exhibit many issues, such as load imbalance, redundant work, and read-write conflicts. And our HoneyComb aims to resolve or relieve those issues and achieve better parallel performance. Before going to the details of HoneyComb, let's first briefly revisit what worst-case optimal join is. Imagine the triangle query. Join three binary relations. If you compute it using binary joins, you end up creating a large intermediate result, the join of R and S. Worst-case optimal join avoids this by intersecting all the relations in a nested loop over the join variables. The result has no intermediate relations and has provably worst-case optimal runtime. For instance, on a triangle query where all inputs have size n, the generic join algorithm has a runtime of big O of n to the power of 3/2, which is optimal. In contrast, the runtime of binary join plan is big O of n square in the worst case. On the right, we can see generic join. Using the variable order x, y, z, it consists of three nested loops, one for each variable. Generic join is easy to implement and quite efficient, assuming access to indexes on the input relations. However, it is unclear how to parallelize it efficiently, while also keeping the optimality guarantees. A natural approach to parallelize worst-case optimal join is to partition the domain of the first variable. In our example, that is variable x. Systems like Logic Blocks and Umbra take this approach. Each thread handles one partition of x, running the rest of the join sequentially. This works, but has serious limitations, as we'll see next. On the sparse data, partitioning only the domain of the first variable makes this approach sensitive to skew, for several reasons. First, when the domain of the first variable has too few values, then there may be fewer partitions than the number of available cores. Second, when the distribution of these values is skewed, causing some partitions to be much larger than the average. And third, even when the distribution of the first variable is unformed, the outputs generated by each partition may be skewed significantly. It is difficult to achieve good load balancing by partitioning only the top variable. Moreover, on the dense data, we observed another issue experimentally, is that the lazy index construction, which is very effective in single-threaded implementations, can become a bottleneck in parallel implementations because of read-write contention across threads when a thread attempts to insert a new value in the index, while others read or attempt to insert the same value. Besides, the try index also tends to be cache unfriendly, which leads to performance degradation. Next, based on the above observation, we will describe the main ideas behind our parallelization of worst-case optimal joins. Our idea is quite simple. We partition across all variables instead of the top-level variables. That means x, y, and z each get split into several parts. Also, we assign each triple I, j, k to each thread or task. In detail, we first split the attribute domains by hashing function into different partitions, and then split the relations based on the combination of partitions of its attributes. For instance, the partition Rij comes from the restriction of the relation R to the product set of AI and Bj partition. Now, during the join in the right figure, each thread identified by the triple ijk just reads only a small slice of each relation, that is Rij, Sjk, and Tik, and works independently. Since the partition considers all variables, not just one, it is less sensitive to skew. In addition, there is no need for locking because there is no contention. Before we describe the details of our solutions, we illustrate here the intuition behind its improvement over the traditional parallelization method. The graph illustrates the workload distribution of the threads on the triangle query executed on the Orkut dataset, which has 117 million edges and 3 million unique nodes. we used 4,096 partitions, each assigned to a thread, which were executed on a server with 60 physical cores. The graph shows the runtime of each thread, measured as it had been executed in isolation, for example, using a sequential execution. The partitions, or threads, are sorted in descending order of this runtime. In the right figure, the blue line corresponds to traditional parallelization of worst-case optimal join, where domain of X is divided into 4,096 partitions, while the domains of Y, Z are not partitioned. As we can see, there are much huge runtime variation across threads. The wall clock runtime, on 60 cores, was a little over 13 seconds. The orange line shows the distribution when we partition each of the 3 domains to 16 partitions, still using a total of 4,096 thread. The load is more balanced, and the overall runtime has decreased to a little over 6 seconds. Finally, the green line shows the partitioning chosen by our system, which is optimal in this case. Now we will quickly talk about the hypercube. Our design is inspired by the hypercube algorithm from the theory community. It partitions each variable and assigns tasks to a multi-dimensional grid of processors or nodes. Each node is assigned by a 3D label in our example, and the relation R is split to big I multiple big J parts. Each of the parts are broadcasted to the other nodes who share the same partial identifiers. But that approach is designed for distributed systems, not shared memory. We adapt and simplify it for multicores and make it much more efficient. In HoneyComb, we abstract the work existed in the original node by the task, and now we can have plenty of tasks which could exceed the number of cores, as long as we dispatch the task to the cores. However, there's no data replication, since tasks or threads can read shared memory. Each relation is partitioned into subarrays, and threads access only the slices they need. It's simple, clean, and it avoids all the communication cost from distributed systems. And we also do not need to include any concurrency mechanisms for threads. Now it's time to introduce our system, HoneyComb. The HoneyComb has 4 main components: optimizer, allocator, preprocessor, and execution engine, which consists of multiple executors. The allocator just manages computation and storage resource for the whole query evaluation, and we will refer to the other components later. In HoneyComb, we mainly process queries in 2 phases. The pre-processing stage is responsible for partitioning, sorting, and indexing. After a synchronization barrier, the join stage performs the optimized join in complete parallel. In our pre-processing stage, we hash partition each relation based on its join variables. To minimize synchronization, we employ a 2-scan approach where each scan operates in a fully parallel manner. The first scan determines the destination partition for each tuple and pre-allocates the required memory space. The second scan then performs the actual data migration. Let's walk through an example in the right figure. For an input relation R, we first generate a partition identifier for each tuple by hashing its attributes using different hash functions and packing the hash values into the array. This step creates an identifier collection A and is done completely in parallel. In the meantime, we calculate the size and the offset of each partition for allocation, which here is just B and B prefix. Finally, as shown by the color coding, we perform the migration into the allocated relation R tilde with full parallelism. Concretely, tuples from R that share the same partition identifier in A are grouped together in R tilde. Once partitioned, the data is organized into multidimensional arrays, and each partition is sorted in parallel to accelerate the later join execution. This process is performed eagerly and, crucially, without any shared state between threads. We benefit from the fact that there exists very effective parallel shared memory sorting algorithm called IPS4O, in-place parallel superscalar sample sort. In particular, our sorting strategy is also adaptive. If the total partition is not enough for fully parallel, we will use the parallel IPS4O sorting algorithms. But if we have many partitions, it's more efficient to run a fast sequential sort on each partition, with all of them running concurrently. Our index structure is called CoCo, short for compressed column layout. It's like a trie, but flattened into sorted arrays, one for each attribute level. Level K of CoCo is a sorted array, consisting of the first K attributes of the relation, which pointers to the next level of the trie. The construction of CoCo is fully parallel, since it happened inside the partition. By replacing the hash-based index with a sort-based one, we reduce the construction time significantly, and this allows us to compute it eagerly. Since it's built up front, we avoid the lock contention that happens with lazy hash tries in other systems. The executor runs a parallel version of generic join. Each thread gets a unique identifier's IJK, accesses the partition of relations based on the identifier, and computes independently. No contention during the whole join procedure. Here, the intersections are done using multi-way merge over CoCo arrays, using different search that decided automatically. Based on the characteristics of Hypercube, the output generated by each thread is not only non-overlapping, but also collectively forms the complete result set. Thus, our results are just written to local buffers for each task. Again, no synchronization needed. Next, we use a cost model to choose good variable orders and partition shares. This helps avoid both load imbalance and redundant computation. It is hard to understand those symbols at short time. To save everyone's time, here just listed the key idea in the slides. It estimates the cost of intersections, accounting for relation sizes and skew, and then sum up the complexity for each given value for attributes. Finally, estimate the summation by the worst-case projected join size. Noticing the cost model depends on the variable order. We could choose the best order to minimize the overall cost. To obtain the minimum cost, we either use dynamic programming for queries with few attributes or use greedy search for the other cases. Further, we extend the cost model to account the partition shares based on a given variable ordering by considering some value will be discovered redundantly if we partitioned on the lower level attribute. Under the extended cost, we prune the possible partition shares heuristically by avoiding both large costs and small partitions. Finally, we measure the evenness to favor evenly distributed partition numbers, but with a bias having more shares on last variables in the ordering. Besides, worst-case optimal join sometimes compute the same intersections over again and again. We could detect these cases and alleviate them. For instance, the highlighted areas at the right bottom algorithms are just repeatedly calculated substructures in the four-click queries. Given the fixed x and y, we observe that the intersection highlighted by the red will be computed again and again over arbitrary variable z. Here we need to mention that the hypertree decomposition cannot realize or prevent these duplications. We detect these duplicated intersections by exploring the dependency among different attributes with relations nexem. Next, we lift these intersections out of inner loops, treat them as independent computation entities, compute them only once, and cache the results of the intersection in local buffer. In the loop body where needed, the cached pre-computed intersection will be efficiently accessed and reused. Theoretically, not all rewriting is optimal. Some of them may even violate the worst-case optimal properties. However, we can still estimate the cost or benefit brought by rewriting and then avoid the non-optimal rewriting by our optimizer. Now we will present the experimental results of our system HoneyComb. We evaluate HoneyComb against several systems: Umbra, Diamond, Kuzu, DuckDB, and Souffle. These represent the general purpose and graph-focused engines. Umbra, Diamond, and Kuzu support the worst-case optimal join while the others not. Also, we list the queries and the datasets used in our experiments. Our datasets include both sparse and dense workloads. In the paper, we also report results on sparse tensor kernels over synthetic data, that is the Loomis-Whitney and Clover triangle queries. In general cases, we outperform the baselines on most datasets and queries. On dense datasets, such as G+ and ORCUT, HoneyComb benefits from rewriting and CoCo, while it efficiently supports lookup and scan over the sorted dense data. Especially on query Q1, Q2, and Q4, our systems outperforms at least 3x compared to other systems. Umbra and Diamond incur an overhead during the construction of the hash trie since most of the subtries are touched and need to be built, while other systems lacks either the support for generic join or enough optimization for join operations. Besides, on sparse data, our rewriting and CoCo index give us the edge, and HoneyComb continues to outperform the other systems. But the gap between HoneyComb and Umbra or Diamond narrows due to their lazy trie construction is more effective for sparse data. Listeners who are interested may consult the paper for further details and discussion on other query, datasets, or systems. To show the scalability of systems, we measure the runtime as a function of the number of virtual cores. HoneyComb consistently demonstrated almost linear scalability up to the maximum number of physical cores, which was 60 on our system. Increasing the cores up to 120 led to no additional performance improvements, showing that the cores were saturated. We also confirmed that the CPUs were at almost 100% utilization at 60 cores. Umbra also shows an almost linear speedup, but slightly below that of HoneyComb. For instance, consider the Q6 4-click query on WGPB. HoneyComb is 1.12 times faster than Umbra on 1 core, but 2.52 times faster on 60 cores, demonstrating that our techniques improve scalability as we increase the number of cores. Diamond just behaves similar to Umbra in most cases, and interested ones can refer to the paper for more detailed explanations. Here, we show how sensitive the runtime of systems is to the variable ordering. The figure shows the runtime for executing the Q6 4-click query on WGPB for all 24 possible orderings of 4 variables. We observe that the bad orders lead to more intermediate results by influencing the number of intermediates. Our optimizer captures the characteristics of intersection complexity and thus choose the almost best order among all cases. We have a similar analysis on the choice of the partition shares. We run the triangle query using 1024 threads and considered all possible ways to factorize it into 3 variables. Here, the x and y axes show the number of shares assigned to variable x and y. Thus, the numbers on Z can be inferred and is shown in the color of dots. Then the size of each dot represents the runtime. Here, smaller is better. From the figure, more partitions on C is slower, but even partition on A and B is faster. Our optimizer could choose the best shares 32 by 32 by 1. This cannot be done by either the original distributed hypercube or the traditional top-level partition strategies. Finally, we just quickly show the results related to rewriting and indexing techniques. On complex queries, rewriting gives us some speedup by avoiding duplicated intersections, and indexing significantly accelerates the access and search operations during join procedure. Moreover, the CoCo index is lightweight. The index size is comparable to the data itself, and the build time is relatively small compared with the query runtime. To sum up, HoneyComb is a fully parallel, lock-free, worst-case optimal join engine for shared memory multicore systems. It is robust, efficient, and scales well across diverse workloads by applying a variety of innovative designs and techniques. For future work, we're exploring faster cost estimation methods, ideally polynomial time, maybe even linear with pre-computed statistics. We're also looking into wider rewriting mechanisms that could explore and reduce more potential duplication or even take over the responsibility of hypertree decompositions. Further, we hope that the rewriting technique can be more closely tied to the cost of other components in the optimizer. That concludes my talk. Thank you all for listening. I'm happy to take any questions.